Good morning, everyone. I'm Hayley. I am a PhD student at UT Austin. And today I'll be talking about our file system, SquirrelFS, and how we use the Rust compiler to check its crash consistency. A storage system is crash consistent if it ensures that data is not lost or corrupted in the event of a crash due to a kernel panic or power loss or other exceptional event. And although this is an extremely important function of storage systems, it's also very difficult to ensure that it holds. Current approaches to ensuring crash consistency tend to fall into two kind of categories on either end of the following spectrum. On one hand, we can test our systems to check that they are crash consistent. This is the most common approach, and there have been a variety of tools developed to test systems in this way, but testing is incomplete and cannot guarantee the absence of crash consistency bugs. It also requires specialized tools because, crash consistency bugs don't tend to occur in normal execution paths. If we want stronger guarantees, we can formally verify that our code is correct by proving that the implementation matches a specification of correctness. This has also been applied to check crash consistency in a variety of storage systems. And although verification provides much stronger guarantees of correctness, it also requires specialized expertise, and development tends to take longer. Verified systems also tend to be less performant than their unverified counterparts. In this work, we're interested in finding an approach that falls somewhere in the middle of this spectrum, where we don't need any specialized expertise or tools, but can still get static checks of some important properties. And in particular, we're interested in a lightweight way to statically check certain crash consistency properties. To do this, we look to the Rust programming language, which is a high-performance and low-level systems programming language that is growing increasingly in popularity. A large reason for this popularity is its strong type system that can statically prevent a wide variety of critical bugs, including data races, memory safety issues, and, as some recent research has shown, some crash consistency bugs. A paper called Corundum that was published in ASPLOS in 2021 presented a Rust crate or library that is designed for persistent memory storage systems and provides a way to statically check these systems for low-level crash consistency properties. For example, a storage system built with Corundum will always have updates made in the context of logged transactions. If we attempt to write code that does not do this, it won't compile. In this work, we were inspired by Corundum, and we use Rust to statically check higher-level crash consistency properties in a persistent memory file system. By higher level, I mean that we want to look at properties that users tend to expect from these systems, like the atomicity of system calls. To do this, we built SquirrelFS, which is a new persistent memory file system with statically checked ordering-related crash consistency properties. These static checks do not require any existing tools or modifications to Rust. It's only relying on features already present in the language. SquirrelFS introduces Synchronous Soft Updates, a new crash consistency mechanism that simplifies the existing soft updates technique. And it uses an API design pattern called the typestate pattern to statically check the order of durable updates. SquirrelFS achieves similar or better performance to other persistent memory file systems while simultaneously obtaining stronger guarantees about crash consistency. SquirrelFS is open source and available on GitHub. For most of this talk, I'll discuss the higher-level design decisions that went into building SquirrelFS, starting with the property that we focus on for crash consistency, ordering. Ordering really underlies all crash consistency mechanisms, because if updates are not made to durable storage in the correct order, the system risks not being crash consistent. To get some intuition for why this is, let's look at a simple example of creating a new file in a file system. At a high level, this consists of 3 operations. We want to create a directory entry to store the file's name, an inode which stores its metadata like its size and where its data is located on storage, and we need to create a pointer from the directory entry to the inode to facilitate lookups by name. Even with just these 3 simple operations, an incorrect ordering can cause a significant crash consistency bug. For example, suppose we create the directory entry first, and then write the pointer to where we plan to initialize our inode. If we crash at this point, the directory entry will point to some garbage uninitialized region of storage, and when the developer or the user tries to read the file or look up its metadata, they will see an inconsistent state. And so this implies that there is an ordering relationship or an ordering rule that we need to follow to be crash consistent. Setting the directory entry pointer depends on initializing the inode. And it turns out that there are dependency relations like this for other operations in file systems as well. And so if we can statically enforce the order of durable updates in storage systems, we can prevent a very large class of crash consistency bugs at compile time. To do this, in SquirrelFS, we looked specifically to the soft updates crash consistency mechanism because it's a natural fit. It derives crash consistency entirely from ordering by tracking dependencies between in-place durable updates and then using those dependencies to correctly order them when they're flushed to storage. However, if you're familiar with soft updates, you probably know that it is notoriously complicated and rarely used in practice as a result. The primary place where it's been deployed is in some BSD file systems, but as of 2023, it was removed from OpenBSD because it was simply too difficult for the maintainers to continue to manage it. We identified two high-level challenges with soft updates and present solutions to make the approach tractable in SquirrelFS. The first challenge is that tracking asynchronous dependencies is extremely challenging for developers. They need to use complicated structures and logic to keep track of what the dependencies are across multiple updates from multiple different system calls. The second challenge is getting this ordering right. Even if we can track these dependencies, the updates still need to be written out in an order that is actually crash consistent, potentially in the presence of reordering by the hardware. To address the first challenge, we observe that this goes away entirely if we can build our system in a synchronous manner, where all of these dependencies are resolved by the time the system call returns. Historically, synchronous storage systems have not been feasible due to the slow access latency of storage devices, but the recent emergence of persistent memory hardware that provides very low latency access to durable storage has provided us with an avenue to build such synchronous storage systems. And so that's what we focus on here. To get the order right, we use an API design pattern called the typestate pattern to statically check the order of durable updates to help developers gain more confidence that they are indeed performing updates in a consistent order. And so now I'll talk a little bit more about what the typestate pattern is and how we use it to check crash consistency. The typestate pattern is a way to encode an object's runtime state in its type. This incurs no runtime overhead. All of this additional information is used only by the type checker and then is erased by the compiler before we run the code. We, as systems developers, are probably used to writing code without typestate. So for example, we might write a function to initialize an inode that looks in pseudocode something like this. It takes a reference to an inode and then we'll perform some operation to initialize it. With typestate, we can attach some additional information to the type of this inode that changes as we update this object on durable storage. The function, using Rust's ownership type system, consumes the input state and returns the new state, which essentially starts to encode a state machine representing how this object changes in this operation. We can define further functions on these objects that specify types in their arguments and expand our state machine further to essentially encode these update dependencies in the signatures of functions that perform durable updates. Now, to see how we can use this to find crash consistency bugs, I'll go through a quick pseudocode example showing how we turn a crash consistency bug into a compiler error with typestate. So we're going to go back to the example of creating a new file, and I want to point out that this code does indeed have a bug in it. It specifically has the bug we saw earlier, where the directory entry pointer is initialized or set before the inode is initialized. So let's walk through this code. We first need to allocate a directory entry and an inode. In SquirrelFS, these two objects start out with a free type state to indicate that they have not been initialized and there are no outstanding rights to them. Then we might initialize our directory entry by setting its name. And this operation updates the directory entry state from free to initialized, which is reflected in its type state. Finally, we might try to set the directory entry pointer, since we have an initialized directory entry. But as we've already established, this is a crash consistency bug, because if we were to crash at this point, our directory entry points to an uninitialized inode. Normally, this would not be easy to find using traditional runtime testing and wouldn't be detectable by a compiler, but with typestate, we get an error that looks exactly like this from the Rust compiler. Not only does it tell us that we have an error before we ever run the code, but it also gives us clear information about the state of the inode that we passed in and the state that it needs to be in before this operation will be crash consistent, thus turning this into a compiler error. Now that we've looked at the type state pattern and ordering for crash consistency, I'll now talk a bit about SquirrelFS's implementation and how we evaluated it. SquirrelFS is, of course, our prototype file system that uses type state checked synchronous soft updates for crash consistency. It's implemented in about 7,500 lines of code of Rust and runs in the Linux kernel using infrastructure from the Rust for Linux project. It has a pretty simple, durable layout that is similar to other persistent memory file systems, and like these other systems, uses volatile indexes and allocators to speed up operations like allocation and lookups. SquirrelFS also provides similar crash consistency guarantees to these systems, providing atomic metadata-related system calls, including rename, which is a very crucial operation for a lot of applications. It's important to note that type state checking is not equivalent to full formal verification. It checks that operations are performed in a specific order, but it doesn't check that the order itself is crash consistent. And so to gain confidence in SquirrelFS's design, we built a model of it and model checked it in the Alloy model checking language. We used the model checker to ensure that various invariants related to crash consistency and correctness hold, even in the presence of multiple crashes. Now I'll talk a bit about the experiments we ran on SquirrelFS. We evaluated SquirrelFS on real Intel Optane persistent memory and compared against 3 state-of-the-art PM file systems. ext4dax as a baseline, as it is the only persistent memory file system in the Linux kernel at the moment. It's a port to persistent memory of the widely used ext4 system. And we also compared a NOVA and WineFS to recent persistent memory file systems. Our paper describes a variety of experiments that we ran. Due to time restrictions, I'll just touch briefly on 2 of them. We're going to look at how SquirrelFS compares to these other systems in terms of performance, and we'll also look at how long it takes to check and compile SquirrelFS. So on this slide here, I have results from experiments on several common file system benchmarks like FileBench and the YCSB workloads running on RocksDB. Each of these graphs shows throughput, so higher is better, and SquirrelFS is shown with a black bar on each of them. And we can see that on all of these workloads, SquirrelFS achieves similar or even better performance to these other file systems, even though alongside the fact that it has stronger crash consistency guarantees. And from these experiments, we conclude that SquirrelFS is competitive in terms of performance, and these additional checks don't add any additional overhead to its runtime. We also wanted to look at how long it takes to compile and check SquirrelFS's crash consistency properties. If we look at formally verified systems, FSCQ is a formally verified file system and VeryBetter KV is a formally verified key value store, we can see that running full verification to prove that they are correct takes quite a long time, on the order of hours with a single thread. In contrast, simply compiling and running type checking on completely unverified systems like ext4dax, NOVA, and WineFS occurs in tens of seconds. SquirrelFS, when we compile it, we both perform its type state checking that checks crash consistency, as well as compiling it to an executable. And we can see that this compilation time is both on par with the other systems, so our additional type state checking doesn't really add any noticeable overhead. And we can also see that our checks proceed much more quickly than a full formal verification pass does. In conclusion, we've presented SquirrelFS, a new persistent memory file system that uses the typestate pattern to statically check ordering for crash consistency. We introduced the Synchronous Soft Updates crash consistency mechanism, and we find that SquirrelFS achieves comparable performance to other persistent memory file systems. SquirrelFS is open source and available on GitHub if you'd like to check it out. Thank you.